question I'm addressing in this talk is whether a classical computer can use the computing power of a quantum computer while maintaining privacy. So this question is particularly relevant to proposals for quantum computing in the cloud. And to state it a bit more precisely, there's a classical computer, which is called a client, a quantum computer, which is called a server, and the client's goal is to have the server run a quantum computation on his data without learning anything about his data. So the client's going to send over some encrypted classical data. The server is going to apply a quantum circuit, which is represented by a unitary U, on the data and send over the encrypted result. And then the client should just be able to decrypt and obtain his final result. This question is called quantum homomorphic encryption. And in the classical world, it's well studied and it's called classical homomorphic encryption. The setting is a little bit different. Here there's a weak classical client and a more powerful classical server, but the goal is the same. The client still wants to use the computing power of the powerful server, but he doesn't want the server to learn his data. And this was first shown to be possible by Craig Gentry in 2008. Now the first question to ask is, can classical homomorphic encryption schemes be used to evaluate quantum circuits? So the same encryption, but instead of a classical circuit being applied on top, a quantum circuit would be. Now, there's a big problem here, and it has to do with an inherent property of classical homomorphic encryption schemes. And this property is that an encryption of a single bit in a classical homomorphic encryption scheme has many different possible encryptions. This is crucial because while the server is performing the computation, he might obtain many different encryptions, and if the encryption is deterministic, then he can learn something about the computation. So the issue is that if there are multiple encryptions for every bit, this seems to prevent the quantum property of interference. So now let me briefly tell you what this property is. And to do that, I'll require the Hadamard transform, which it's the quantum Fourier transform. It's a reflection by pi by 8. So it maps 0 to 0 plus 1, and it maps 1 to 0 minus 1. So now to see the property of interference, let's see what happens when you apply the Hadamard transform to 0 plus 1. So we expect the output to be 0. And what interference is saying is that elements of a superposition representing the same bit string but with opposite amplitudes must cancel. So what I've written here is I just broke down the Hadamard transform by applying it to 0 and 1 separately. And what's happening is that the two ones just cancel. But now if we use homomorphic encryption, classical homomorphic encryption, in the most naive way by just encrypting the zeros and ones, this might not work out, because if the two encryptions of one are different, they won't cancel, and then I won't get interference. So this was the main property with just immediately extending classical homomorphic encryption schemes to quantum circuits. And because of this difficulty, the definition of quantum homomorphic encryption was weakened to allow a quantum client rather than a classical client. So now the quantum client is just weaker than the quantum server. And in this model, there was a lot of progress. And it started with something called blind quantum computation, which is almost the same as homomorphic encryption, but it allows multiple rounds of interaction. And in 2005, Andrew Childs showed this was possible information theoretically, which stands apart from the classical setting where all the results are computational. And in 2008, this was improved so that the quantum client requires only a single qubit. And this technique is also information theoretic. It's based on teleportation techniques. Then in 2016, Dweck, Schaffner, and Spielman went back to the question of homomorphic encryption with a quantum client. So they removed interaction, and that was also possible, but it became computationally secure. Now, weakening the definition to allow a quantum client allowed us to make a lot of progress in the area of delegated quantum computing, but there's a major issue with a quantum client. And that's, okay, the point of the quantum client is to create quantum evaluation keys, which he sends over to the server, and that helps the server run the computation. But the issue is that the number of evaluation keys corresponds to the size of the circuit. Moreover, quantum evaluation keys cannot be reused. So what this comes down to is that each time the quantum client, wants to delegate a quantum computation, he has to run a polynomial-sized quantum circuit. So this might be a simpler circuit than the server, but we'd still like to avoid the fact that he's running this polynomial-sized circuit. So in this talk, I'll go back to the classical client and quantum server. And what I'll show is that certain classical homomorphic encryption schemes can be used to homomorphically evaluate quantum circuits. So that's what I said was hard at the start, but I'll show that if the homomorphic encryption scheme satisfies certain properties, we can get around those obstacles. Okay, and the advantage here is now I have the same properties of classical homomorphic encryption schemes. Of course, the keys are reusable, they're classical, and then things like circular security, which can be assumed in the classical setting, can also be assumed here. This scheme is the first to allow blind quantum computation between a classical client and a quantum server, since all the previous models were with a quantum client. Okay, in this talk, I'm not going to have time to cover the full protocol, so instead I'll show you the main building block, which is called the encrypted C0 operation. And this is what all of quantum homomorphic encryption boils down to. So to introduce this, I should first tell you what the C0 is. The C0 is a quantum gate, and it's just the reversible XOR gate. So it takes as input 2 bits, A and B. These might be in superposition, and it just XORs A into the second register. Now, so like I just said, in quantum homomorphic encryption, the server has to be able to apply something called the encrypted C0 operation. What that is the server is given a classically encrypted bit S, and he must be able to conditionally apply the C0 operation based on the bit S. Okay, so that means he's either XORing A into the last register or not, but this is based on an encrypted bit which he can't see in the clear. Okay, so this is the encrypted C0 operation. Now, as I've written it, it's not possible, because if he could apply it to an arbitrary 2-qubit state, of course he could set A equals to 1, B equals to 0, learn the bit S, violate the security of the classical encryption scheme. So what's actually going to happen is when he applies this operation, the output will be encrypted. And for those who know, I'm going to use the Pauli one-time pad. For those who don't, I'm not going to talk about this in this talk, and it shouldn't be relevant. Okay, and this reduction of quantum homomorphic encryption to the encrypted C0 operation is not new to my work. It was used in all the previous papers, but in order to allow the server to implement this operation, the client had to send the server more quantum states, and that was part of the evaluation key. So the point is, here I'll show that the classical encryption is enough, and to do that, I'm going to rely on trapdoor claw-free functions, like Thomas just described in his talk. So let me just briefly recap what he said. A trapdoor claw-free function pair, F0, F1, is a pair of injective functions with the same image. There's a trapdoor, which allows for efficient inversion. Claw-free means that without the trapdoor, it's computationally difficult to find a claw, which is a pair of overlapping pre-images. Now, in the paper with Zvika, Paul, Thomas, and Umesh, we introduced this quantum advantage, which was used in the randomness paper, and it allows a quantum machine to sample a random image Y and create a uniform superposition over the corresponding claw. And he does this by applying the function in superposition and then just measuring the output of the function. And just to recap, he can either measure in the standard basis, obtain x0 or x1 with equal probability. This doesn't give him a great advantage because a classical machine could sample the same things. The quantum advantage comes in because he can measure in the Hadamard basis. He can obtain the string D, which satisfies this equation, which has to do with both claws. And the point is that the quantum computer can do either of these challenges at will. He can choose to measure in the standard basis or choose to measure in the Hadamard basis. And in the paper, we showed that classically, a classical machine cannot choose to do either of these two tasks, because then he could do both and violate this hardcore bit, which says that he can't hold both a pre-image and an equation D at the same time. Okay, so this structure was used in the randomness generation paper, and now I'm going to use something similar for homomorphic encryption. So now I'll show that if a bit S is encrypted in a special form using a trapdoor claw-free encryption, then this encrypted C0 operation is easy. So let me first tell you what that means. So what's a TCF encryption of a bit S? I'll start with the trapdoor claw-free function pair, but I've split up the domain, so the first part is a bit, the second part is a finite set R, the image is a finite set Y. And the first two conditions are just saying that it's trapdoor claw-free, but I've split up the claws, so mu0 is a bit, and R0 is in the set R. And then the part that makes it an encryption is that each claw hides the bit S. So for all claws, if you take the XOR of the first bit of the claw, that is the encryption of the bit S. And that's why I'm calling it an encryption, because in order to recover the bit S, a machine would have to find a claw. Okay, so now given this special encryption, let's see how to do the encrypted C0 operation. This is a C0 operation conditioned on S. I've simplified it a bit from the previous form. In the previous form, there was an extra bit B, and here I've fixed it to 0 just for simplicity. Okay, now how the server does it, he uses this encryption of the bit S, which is a trapdoor claw-free function pair. And then, just like before, he samples a random Y, and he entangles the starting state, which is this summation over A, with the corresponding claw. Okay, and he does this just like he did in the previous slide, in the previous few slides, where he applies the function in superposition, but now it's entangled with this state. So he applies either F0 or F1, depending on the first qubit. And now when he measures that final register, the state will be entangled with a claw. Okay, now what's the point of this? Entangling the state with a claw is essentially applying the encrypted C0 operation. And to see this, so I've just written this equality here, but note that mu0 is equal to mu0 XOR A dot S, because A equals 0, and mu1 is equal to mu0 XOR S, because of the encryption property, because F0, F1 hides S in each claw. So essentially, all the server had to do to apply the encrypted C0 operation was entangle the state with a claw. Because now on the right-hand side, you can see it's almost the same as the top line, but it's off by mu0 and RA. So he's applied the operation, but it's hidden by mu0, R0, and R1. And remember before I said that there has to be a suitable encryption? That's what mu0, R0, and R1 are. They hide the bit S. So mu0 is just a classical one-time pad, and it's necessary to avoid the server breaking the encryption. And R0 and R1 are kind of like the quantum versions of the one-time pad. They're necessary because the bit S is stored in superposition. So for those people who know, mu0 just turns into an X Pauli one-time pad, and R0 and R1 can be turned into a Z Pauli one-time pad by doing the Hadamard transform. Okay, so far, what I've showed you is that classical homomorphic encryption schemes, which have this nice trapdoor claw-free structure, where the encryptions are actually TCF, trapdoor claw-free functions, can be used for homomorphic evaluation of quantum circuits. But there's one step left, because I need to link this. Do there actually exist classical homomorphic encryption schemes with this trapdoor claw-free structure? In other words, if the server starts with an encryption under a classical homomorphic encryption scheme, can he produce this TCF encryption by himself? So can he produce these functions F0, F1? It turns out that if the classical homomorphic encryption schemes satisfy certain properties, then the server can do this. He can begin with an encryption, and he can produce the trapdoor claw-free function pair. More specifically, there's a specific scheme that I can construct, which I construct by combining two existing classical homomorphic encryption schemes by Gentry, Sahai, and Waters, and Gentry, Pikert, and Vaikunthanathan. Okay, so to conclude, I began with saying that quantum homomorphic encryption boils down to something called the encrypted C0 operation, which is just the ability of the server to convert a classical encryption into a quantum operation. And then I showed that the server could perform this conversion if the bit was encrypted in a special way using a trapdoor claw-free function pair which hid the bit S in each claw. And the last thing I said was that there exists a classical homomorphic encryption scheme which allows the conversion to a trapdoor claw-free function pair. To conclude, this classical homomorphic encryption scheme can be used for evaluation of quantum circuits, thereby giving a way for a classical client to blindly delegate a quantum computation.
Control nut.
Yeah, that is exactly the problem. So what happens is if you want to apply a non-Clifford gate, so usually they all use this Pauli one-time pad structure, right? And the problem is that you can't apply a non-Clifford gate on top of a Pauli one-time pad. If you try to do that, it turns into a correction which depends on the one-time pad. But that correction is this C naught. So it's a C naught correction which depends on the one-time pad, but he's given the one-time pad in an encrypted format. So what he needs to do is take this encryption and convert it so he can correct which results from the Toffoli gate. Does that make sense?
Sort of. So you could do a T-gate.
Yes, because so the T-gate maps, the T-gate results in a Clifford correction, so everything boils down to the server being able to apply this Clifford correction based on a bit that he doesn't know, which is the one-time pad. Okay. Yes.
So if you wanted to sort of take a step beyond, you wanted to verify this delegated computation, does the quantum aspect, does that stay, can that be done entirely in the classical realm, or is that also needed another step of classical interaction?
Okay, so in the classical world, they can extend homomorphic encryption to verifiability. And that's, I think what that boils down to is because they can make the computation deterministic. I can't extend this scheme to verifiability. So to do that, I need to use the other verifiability result, which is totally separate. And right now, I don't know how to take just these techniques and use them for verifiability.